Okay, so we're doing this again. This is going to be the reviewer for the triangle similarity. Now, this is actually really related for previous topics. So let's get started. So we all know, first let's go describe a proportion. So what is a proportion? Well, a proportion is just two ratios that when simplified, it will result in the same value. So we all know ratios like 2 is to 3, 6 is to 7, and 8 is to 10, for example. These are what we call ratios. But what can we say when things are proportional to another? Well, for a proportion to happen, there has to be at least two ratios. And we need to apply a fundamental law to ensure that these two ratios are indeed proportional to each other. For example, let's try 2 is to 3 and versus 6 is to 8. Now, 6 is to 9. Let's do this. Now, we need to do a fundamental law where it states that the product of the means is equal to the product of the extremes. But what are the means and what are the extremes? These two are called the extremes, the one at the very end of each one. So when you're dealing with a proportion, it looks something like this. So these are the extremes. And the one at the middle, the two middle numbers, are what you call the means. So fundamental law states that 3 is to 6. So 3 times 6 is equal to 18. And 2 times 9 is also equal to 18. Hence, this is what we can have a proportion. This is considered a proportion because the sum of the product of the means is equal to the product of the extremes. That is what we call the fundamental theorem of proportionality. And there's a lot of other ways we can express this as well. We can also express these two as a fraction, 2 over 3 against 6 over 9. And as you could see by simplifying it, this is correct. And once again, as you could see, if we cross multiply, we get the means and the extremes, and they are still indeed equal to 18, as I'm highlighting over here. Now, that's all good, but what if we have to now go through the triangles as well? How are these proportions related to triangles? Well, we're gonna try to use other theorems, and yes, this list is very out of order, but I will try my best. This similarity of figures. We're gonna illustrate the similarity of figures next. The similarity of figures is not restricted to just triangles. It can be any shape, in fact, but the most common you have to look out for are triangles, rectangles, and squares. So, for triangles, we're gonna hold on to that later because we can use these three theorems over here, which I'll show you in a bit on how to solve. But we have to prove that we have to go here first. That illustrates the similarity of figures. So first, how do we say that two are similar? Two are similar. So once again, we can always just use, this is for rectangles. We can use these as rectangles if we just sub two numbers for the lengths and widths respectively, such as length 1 is to width 1, and is equal to length 2 is to width 2. And then we can also use these theorems to prove if they're proportional. So let's take, for example, these two rectangles, these two rectangles, a bigger one and a smaller one. So this smaller one's length is 5, let's say 5, and the bigger one is 15. Meanwhile, the width of the smaller one is 3, so we're gonna find, and the length of this one is going to be 9, width is gonna be 9. Now, are these two similar? We'll see. So we know that length 1 is 15 and width 1 is 9. That's the first rectangle. Meanwhile, the second one is with a length of 5 and a width of 3. It is important to keep these two in order, otherwise your proportion will be off and it will be incorrect. So if you put length first for the first one, it also has to be length first for the second one, width first for the first one, width first for the second one. We have to apply this because even just one swap can lead to a wrong number. So let's try to apply these this one. So 9 times 5 is indeed 45, and so as 15 times 3. Therefore, these are indeed proportional rectangles. And I'm sorry about that, but squares are always proportional to another because all of their sides are equal. All of these are equal, hence are always proportional. So remember, squares are always proportional. No matter what. If it's not proportional and claims to be a square, well then those are not squares. Anyway, I'm gonna erase all of this. It's kind of just rough work here, but that's how we illustrate the similarity of rectangles. Anything other than rectangles, squares, and triangles, it's honestly unrealistic as we have not covered those topics, so no need to worry about the similarity of a pentagon, an irregular figure. You don't have that. We only have that in like contest questions, which we will not do. So with that, we did illustrate the similarity of a figure, but how do we, well, name these figures? So I'm gonna show you a little bit of a trick, and we're gonna only use triangles for this example. Now, what do we do here? Which similarity statement refers to the triangles given? This is another example of illustrating this triangle similarity, and it might be tricky at first, but here's a tip. When looking at triangle similarity in these terms, it's usually just going to be a right angle. So you want to use that right angle to, well, kind of as a marker somehow. I'll show you. So first, I want you to draw the triangle, trace the triangle. So let's say AD and then DC. So therefore, triangle ADC. And now you're asked to find out what is the one that's congruent to it. Well, as you can see over here, let's rotate the figure. We have what we call, this is the hypotenuse in blue. And then this one that I'm highlighting right now is called the shorter leg. Meanwhile, this one is called the longer leg. So which did we use to form this name? We used the shorter leg first, then the longer leg. Now, to find the similarity of, let's say, BDC, or this triangle over here, we need to apply the same logic. So over here is the right angle over here. So therefore, we need to find the shorter leg and connect those. So CD, and then connect it going here. So C, D, and B. Therefore, using that statement, we can say that triangle ADC is similar to CDB. Now, let's try to use an example using proportions. This is going to be another tricky one, and yeah. Well, let's see. First and foremost, which of the following is not a proportion for these given similar triangles? So I need to show you the options. I'm so sorry. As I've shown earlier, we can express proportions as fractions as well, not just ratios. So like this. As you can see, we have a correct answer here, which is not applicable, a non-applicable proportion for this given similar triangles. But it seems overwhelming and confusing with the amount of letters. How do we differentiate them? Well, once again, just like how I did here by naming them shorter leg, longer leg, remember, if a shorter leg is here on the top and a longer leg is bottom there, it has to be the same pattern here. So, let's try this. On the first option, we're given AD and CD. AD is here and CD is here. Therefore, this triangle is being referred. Now, AD is the shorter leg, so we can say, I'm just going to use SL. SL over AC, which is the H, hypotenuse. Now, let's cross-check again. What is CD now? CD is indeed the shorter leg, as you could see. And BD. BD is indeed the longer leg. Sorry. Is it the longer leg? Yeah. Sorry. Is it CD over BD? Yep. CD. So we have an S shorter leg over, what's this one? Is this even a... Yeah. So this is shorter leg over... Oh, sorry. This is not the hypotenuse. This is gonna be the longer leg. So yeah, because I'm so sorry. But we got CD. So CD. So AD and CD, that's both legs. So that's shorter leg over longer leg. And for the second one, that's gonna be CD over BD. So CD, shorter leg, and BD, which is the longer leg. So that is correct. This option is correct because it's just the shorter leg over the longer leg. Now let's try this one. AB and AC. So AB and AC. This time it's referring to the hypotenuse and over the shorter leg. Why? Because as you can see, the right angle is over here. And this is the shorter leg. This is the AB, which is on top. So that's the hypotenuse. And this is the AC at the side, which is the shorter leg visually, as you can see. So therefore, that is, so far, that's our equation. Then this time, let's try that again. AC over AD. This time, we're referring to this triangle over here. So, it's gonna be AC, which is a hypotenuse, and CD, which is the longer leg. Sorry, CD? No, AD. AC over AD, which is the hypotenuse and the shorter leg once again, giving us another applicable proportion. Next one is AB and CB. So AB and CB. This time, it looks like to be the hypotenuse and the longer leg. So H, hypotenuse over longer leg. And then once again, CB and DB. So CB and DB. Now let's rotate it a bit, and once again, DB is the longer leg and CB is the hypotenuse. Therefore, they do follow the same proportions, which means all three of these are correct. And I'll explain to you why this one is the one that isn't applicable. AD and BD. Now, that's already immediately wrong because they're not in the same triangle. So we can't even define this because one is a shorter leg and the other one seems to be a longer leg. So it's already wrong to begin with. It's not referring to any triangles. And BD over AC. Now, that's just two completely different parts, as you can see, because this one is not part of any triangle. You can't define a triangle from these two lines. So, since you can't define a triangle from these two, this is the one that isn't applicable. And that's one of the harder ways to illustrate the similarity of figures. But so far, that's the two ways I know of. If you know any other questions, I can answer them. But so far, this is what we have. Now, it's time for where the proving and a little bit of fill in the blanks come in. Friendly reminder that you do not have to memorize all these statements, as there will just be a fill in the blanks and you'll be given options similar to like a word bank, if you know what that is. So once again, you don't have to go through the extreme extent where you have to memorize this word for word. You just need to know where these phrases go to. So as you can see over here, we got 3 theorems. Now the thing is, I can only find problems for 2, and plus SSS is so easy that you might as well just rely on the lengths and properties of triangles to figure that one out as well. So I'm only going to be covering SSS theorem and AA theorem, but I will be explaining you how to get SSS similarity theorem. Now, SSS happens when usually you're given two triangles and they're proportional to another. So let's say 3, 4, 5, and 6, 8, 10. If you substitute the sides, let's say AB and then DE, so like AB and DE is equal to, let's say, ABC is equal to DEF. So, and then you put, let's say BC over, wait, did I call, sorry. Sorry about that. I just glitched. But let's try BC over EF. So if you plug in the numbers, once again, it's going to be 3 over 6 is equal to 5 over 10. Now I'm gonna check if I have a worksheet problem for that, but as you can see, take a look at it first. So this is going to be our AA. Try to see if we can find, if we can tell it here. Let's see if we can find it. And we also have this one, this two statement for SAS. So let's see if we can find an SSS theorem problem, but it's probably not gonna happen. But either way, remember that for SSS and all other theorems that these have to correspond, and I will tell you why later. As you could see, we have corresponding. There's a lot of corresponding there. Corresponding. I'll explain to that why. So let's start with AA. First and foremost, we are given that C and DEA are right angles. So right angles. So that's the given. Remember, when proving, it's always going to start with the given. Now, for analyzing the figure, we got C and DEA. C and DEA are both right angles. So, and therefore, we can say that right angles are congruent. Why? Because right angles are always 90 degrees, and that's given. Now, this is where it gets a bit confusing. So we already proved that one of the angles exists. So that's angle 1. But how do we know that angle A is equal to itself? How do we do that? Well, we have two triangles here. Triangle ADE and triangle ACB. And as you can see over here, triangle ACB has this angle A, and the smaller triangle, triangle ADE, also has this angle A. Therefore, angle A from both triangles, which is being represented here, is congruent by reflexive property. So therefore, we have, we have this one. We prove AA similarity theorem. And once again, we put ADE, and we're going to name this again, ADE. So we run through the hypotenuse and then the shorter leg, and then same here by naming it again. So we want to ABC. So we got to go by the hypotenuse and then the shorter leg. That's ABC. So that's the AA theorem. And corresponding, this please note this down. Corresponding sides, corresponding sides of similar triangles are proportional. So this is AA theorem once again, because if two angles are congruent in two triangles, those two are similar. Remember, two corresponding angles in two triangles prove that they're similar, corresponding. So, using this, we can then therefore come up with a statement. AD sorry, let me write it down first. And ADBC, AB and D, right? DE and BC, yeah, correct? Yeah, I think it's correct. I'll just make sure. Hold on. So yeah, it is indeed correct. So we need to correspond, because remember, AD over AB, right? Yeah, AD over AB. As you can see, they're corresponding, so they go above each other. So AD is a hypotenuse over AB, which is also a hypotenuse. So the two hypotenuse is also proportional to the DE. DE is the shorter leg, as well as the CB, which is also the shorter leg. So these are proportional. They share the same proportion. Yes, correct. So, and by cross multiplying, we get AD times BC is equal to AB times DE. And that is what we call the fundamental law of proportion. Right there. And that right there is the answer to that one. Let's now try for SAS. So we know that BA over IA equals RA over NA. BA over IA, which means these two are, I'll just use these markings to prove that they are, to mark that they are similar, or what do you call this, similar? Yeah, similar. So these are similar, not congruent for this case. So we're also given that RA and NA are also similar. So what do we do now? Given this information, what we have the reason definition of vertical angles. So we have the given now and we've illustrated. So vertical angles, once again, are just angles that are, well, I don't know how to describe them, but an example of them would be this one, the one in green. So we need to trace the lines. So let's run through the yellow first. So BA, and then run through the red, R. So angle BAR is congruent to, let's run through the yellow first. So IA and then red, N. Angle IAN. Sorry, not congruent, not yet. BAR and angle IAN are vertical angles. So once you see this definition of something, just point out which angles or which sides are you referring to. So just say, oh, side A and side B are, let's say, opposite sides, or B, in this case, BAR and IAN are vertical angles. And if you're asked to find the reason, just put definition of vertical angles. Now, this is also given that BAR is congruent to IAN because vertical angles are congruent, or vertical angle theorem. They are both the same thing. Seeing as that we have proved that since we have proved that these two are proportionate from the given, and we've also proved that these two angles are exactly the same, therefore we have two sides and a sandwich in between them, an angle, which all correspond to each other. Therefore, that's the definition of SAS theorem. Two sides and sandwiched in between them, one angle, that all of which correspond to the other triangle, and the angles congruent. Therefore, we can say that triangle BAR is indeed congruent to triangle IAN. And since we're asked to prove that B is congruent to I, and yeah, we are correct, as B comes first here and I comes first over there. Therefore, angle B is congruent to angle I because the corresponding parts of these names are correspond to the other triangle. So as you can see, so therefore BA is corresponds to IA, IN corresponds to BR, so on and so forth. Now, let's continue our proof. We have proved the SAS, but let's go all the way until we hit something like this, just like we did in the last example. So, B is congruent to I. Angle B is congruent to I. Once again, BAR and IAN are vertical angles. Once you see just naming two angles, just put the definition. Definition of vertical angles. Then, you need to identify which vertical angles are congruent here. Because vertical angles are congruent, but which one? So once again, backing up from this statement too, we can say that BAR is congruent to angle IAN. Therefore, once again, since we're given this statement and from the previous statement, we can also say SAS theorem here. Then once again, we have to pull out the what do you call this? Okay, yeah. I have to write it down. RA RA over NA is equal to, so RA, that's a shorter over longer side, I believe, is equal to BA over IA. We need to make sure that all of these are in order so that when we cross multiply, we get this. So, therefore, using this statement right here, we get the fundamental law. That's another fundamental law of proportion. And just like that, I have covered I've proved the similarity of triangles using all three technically. You just need to look out the numbers for SSS. If you have any sample problems you could give me for SSS, I'll be glad to make an extension video. But so far, I've looked through all the presentations. We just have SAS and SAS and AA for proving. So therefore, we can add another to this. Right there. A big chunk, honestly. So let's just connect these two. Alright, we're now to what I consider the last part of the study guide, because honestly, after looking and reviewing through the slides, all of these four remaining topics, they're just really different ways to word them, as they're all related. Usually I just take off one at a time, but once again, I managed to take out four at once here, and I might as well just do the same. Now, the thing is, for this one, the applies theorems on similarity of triangles and right triangles, that is actually surprisingly, you can also just use these three. You just need to be careful about the extra details over here. So we can kind of tick off that. We just need to focus on these last three. So right angle similarity theorem, it can also use these three subjects. So we'll see about that later. But what I want to focus on is the special right triangle theorems. So first and foremost, we have two types of main triangles we need to look out for. A 45, 90, 90 triangle. So this is, and a 30, 60, 90 triangle. So once again, this is going to be 45 degrees, 90 degrees, and 45 degrees. Now, we all know about Pythagorean theorem. We all know that. But what is special about these right triangles? We can always use the Pythagorean theorem to solve these, but there's a trick if they're stated in the exams, that it's something like this. So let x equal the side length. So x, and x square root of 2. That will always be true as long as it's given these angles are the measurements. Similar here, if you're with a 30, 60, 90 triangle, that's going to be x, 2x for the hypotenuse, and for the longer leg, it's x square root of 3. So how do we apply this then? Well, let's just keep this on the board right now. So we have the theorem for the first type of triangle and the theorem for the second type of triangle. So these are the two that we'll encounter, and I will apply them right now. Okay, so before we solve these problems, let's have a little bit of a warm-up exercise. So we know that Pythagorean theorem is this one. It's the good old famous a squared plus b squared equals c squared, where a and b are the legs and c is the hypotenuse. Sorry, a squared plus b squared equals c squared. Similarly, by transposition, you can also say c squared minus a squared equals b squared, and c squared minus b squared is a squared. Now, let's try to visualize that. Keith and Kevin started bicycling from the corner of Manga and Bayaba streets. So let's just ignore the names, but remember, first and foremost, it's important to note that these streets are perpendicular to each other. So these are 90 and 90. Now, let's say Keith went 12 meters to this direction. So Keith is now 12 meters to this direction right here. And we have a right angle here because these streets are perpendicular. And at the same time, we also have Kevin, which went up north 5 meters over here. So remember, the order doesn't matter because we can apply the theorem either way. So we want to know how far apart are they. So we're going to represent those by these 2 points. Now, remember when far apart were they? Remember that you have to use only one line. So you can't just say 5 plus 12 is 17. So no, it has to be one continuous straight line like this. So how do we calculate for the newly drawn green line in this scenario? As I've stated before, it's a right triangle, and for any square triangle, we can apply the Pythagorean theorem. So let 12 be a. So we have 12 squared. So 12 squared plus b, which is b squared, so 5 squared, is equal to c squared. By simplifying, we get 12 times 12 is 144, and 5 times 5 is 25. That's equal to 169, which is 169 is equal to c squared, and just square both sides to find that 13 is indeed c. You can square root this, by the way. It's a little bit tricky because we got 13. It's a prime number. You can't really see it, but just trial and error, and it'll eventually work out. Therefore, the answer to this question is 13 meters. Traditionally, that's how we solve Pythagorean theorem problems, and we can even use this to prove that this is a right angle. Otherwise, this would not come out to true, and this angle would not be right. So if this was 6 and there was a right angle here, right, that would be wrong because it wouldn't be equal to c squared. Oh, sorry. So, yeah, correct. So if I just put 6 here but no marking here, this isn't a right angle because if we do a squared plus b squared, it will not equal. Because 12 squared plus 6 squared is not equal to 13 squared. Let's try to prove that, actually. So let's imagine that we have this given measurement, and instead, we're tasked to find out if it really is a right angle. And this is how we prove the Pythagorean theorem. So 12 squared plus 6 squared should equal to 13 squared. Let's simplify all sides. So 12 squared is once again 144 plus 6 squared, that's 36. That's equal to 169. But we run into a problem here. 144 plus 36 is 180, and 180 is most definitely not equal to 169. What happens if we encounter this? That means that Pythagorean theorem is not applicable to this scenario. Therefore, this is not a right angle. So that's only for very specific cases, but there we go. We proved the Pythagorean theorem. So the answer to this question is actually 13 meters. But there is a shortcut in some cases to find the sides immediately. How's that? So let's take this theorem for example. We know that a 30, 90, 60 triangle will result in the following values of the sides. So we just need to substitute them. So we know that this long leg is x raised square root of 3. And y is just 2x. X would be the base here, which in this case is equal to 8. And then just substitute 8 for all sides, which means we get 8 square root of 3 and 16. Because 8 times 2 is 16. Now, once again, same thing here. We got a 90, we got a 90 over here, we got a 30 over here, and a 60 over here. So it's a little bit tricky this time because it's tilted, but we actually don't have, we have the base, right? Yep, the base is 1/2. So therefore, this is 2x, and this is x square root of 3. Therefore, we have 1/2 times 2x, so 1/2 times 2 is just 1. And we can just do 1/2 3 square root of 3. Or can we do something? I'll find out. But that's so far the correct answer. 1/2 square root of 3. Oh, sorry. I think it's or square root of 3 over 2. Yeah, square root of 3 over 2. Then, once again, applying that theorem here, it's, once again, we have 14 for the base. So 14 is our x. And we have x square root of 3 and 2x for the longer leg and the hypotenuse respectively. So once again, just plot in 14 over here and copy paste the square 3. And 14 times 2 is 28. Now, they didn't give us any exercises for this one because as you can see, just by looking at it, it's very, very easy. This is where you can get messed up, and it actually messed up me a few times, so let's be careful there. And with that, honestly, we're basically done. I mean, basically done as in, we've used the special right angle theorems, definitely. We haven't used it in proving, but it's basically the same anyway. We definitely applied theorems and on similarity of triangles and right triangles definitely throughout this session here. And we did a while ago prove the Pythagorean theorem. And yeah, congrats, we're done. I wish. Because I suspected that this gap over here is actually where the applications of these come from. So yes, they have bamboozled us, and we need to make an extra part of the video. So it's 7:05, I'm going to take a bit of dinner, and I'll be right back ASAP to get this video done by tonight. Well, actually, it's not all that bad, but it's still pretty crucial that they missed quite literally the end topic, which is the application. So definitely need to work on that. So we're gonna now use real-life problems to find similar triangles, I guess. Now, please do note that once you immediately see a word problem on the test, assume that there's some sort of similarity. Assume it. No need to prove it, just assume it immediately. Now, these can get a little bit confusing, so let me walk you through it. Problem 1. A man 6 feet tall casts a shadow that is 10 feet long. So we have a man over here, which is 6 feet. Then we also have the shadow, which is 10 feet. So let's just draw a little shadow over there and say that that is 10 feet. Then the end of his shadow coincides, which means the end of a shadow cast by a building, which means right immediately after this shadow over here, we also have another 128 feet of shadow. And then we got the building over here, which we need to find the length of. From this, it's quite confusing, but once again, let's trace down the lengths. So let's represent them as lines. So the shadows, then we got the heights of the building. Let's use a different color, the heights of the objects. And as you could see, these are correspondent to each other. The shadows correspond to each other. So we can use the ratio that 10 is to 128, or 128 over 10. I think, yeah, well, sure, let's use 128 over 10. 128 over 10, so that's the shadow of the building and the man respectively, is equal to the x over here, which is we don't know, that's the height of the building, over the height of the man, which is 6. Now it's gonna get a little bit confusing here, so yeah, buckle up. So first and foremost, we actually need to get our calculators for this one, because 128 times 6, so we're not really gonna, no, let's not use a calculator, let's solve for it. 128 times 6, that is 48, 12, 4, 16, 1. So it's gonna be 768. 768, and then we get 10 times x, which is just 10x. Then divide both sides by 10 to get 76.8 equals x. And that is the height of the building, 76.8 feet. So yes, that's how we use it. Let's try to use it once here again. A 12 centimeter rod is held between a flashlight and a wall as shown. So we have a 12 centimeter rod. This is not the width of the rod. Definitely not the width of the rod, guys. Not the width of the rod. So we got the we have the 12 over here. This is 12. I'll use a thinner brush. 12. And we have a find the length of the shadow. So we don't know the shadow. That's our x. And then we do know that the shadow, the distance between the shadow, find the length of the shadow on the wall if the rod is 45 centimeters. So the rod to the shadow is 45, and we do know that this gap between the rod and the light, the rod, the rod and the light, right? Find the length of the shadow. Not yet. Whoa. Oh my. Okay, sorry guys. Sorry. My apologies for that. Sorry. But we got a 45 centimeters, the rod. Find the length of the shadow on the wall if the rod is 45 centimeters from the wall. Sorry, this is wrong. 45 centimeters from the wall. And 15 centimeters from the light. Now, once again, we can just use the rod. And rod over gap from light. So that's 12 over 15. And then we also have the shadow over here, which we also need to add this. So it's gonna be 60. Because 45 plus 15 is 60. Because we're making a big triangle here. So you got a small triangle over here, like a small triangle, coinciding with a bigger triangle. It's not really accurate, but you get the point. So therefore, since this is x, right, we do 12 times 60, which is, if you put in the calculator, that's 720, is equal to 15x. And by dividing, we'll do long division. So that is okay. It's gonna be 48. So is that right? Yeah, 48. Let me just check. But yeah, we got 48 feet. And with that, I did confirm that it was 48. I was a bit confused, but hopefully you still got my solution. But yeah, that is just how it really goes here in math. It's very confusing, and I did try to rush it because it was urgent. I just realized that some of you have the test tomorrow, so I just got home and immediately started working on this nonstop. Once again, thank you so much for watching, tuning to the end. I hope this helps, and I hope you pass your test. And I'll be making sure to take care of myself because, kind of going crazy so far. But thank you for staying all the way into at the end. Once again, thank you so much. And I'll see you in the next guide. Bye-bye.